regression next up. We are almost through, guys. We are almost through. So regression is next up. The pattern here is a relationship between the input and the output. So the output, very similar to classification, but the output now is not categorical, but it's continuous. Yeah? So we want to predict a continuous value rather than a category. And the task, of course, is to model this input-output relationship. Yeah? So the relationship between the input, the features of the observations, and the output, which is the predicted value. Yeah? So, for example, we would like to, I don't know, predict the minutes of delay of, I don't know, the Deutsche Bahn train, depending on, I don't know, the weather and so the temperature and humidity and rain and stuff like that, whatever. Yeah? Of course, again, we have to make a lot of assumptions about the type of relationship. Is it a linear relationship, like depicted here in this image, yeah, between the input or the output, or is it a nonlinear thing? Yeah, and there are a lot of popular methods out there. So linear regression, as the name suggests, tries to model the whole thing as a linear relationship. Yeah, so the classical linear regression is a regression line, or in a multidimensional space, a regression hyperplane. If it's nonlinear, we can apply polynomial regression. So in that case, it's not a line what we try to fit to the observations, but a kind of polynomial function, yeah? Like a hyperpolyd or stuff like that. Or we can try to come up with a kind of piecewise linear regression. So we try to cut the input into pieces and then approximate each partition, so to say, each piece with one specific linear model. So that may so we may have then maybe a linear model here in that part here in this lower left part here, which is this one maybe, and then another piece which is have a different shape and a different slope and stuff like that. Yeah, so that would be piecewise linear regression. Regression trees is an extension of these piecewise linear regressions, because sometimes it's not clear where to actually partition the inputs. And then there is logistic regression, which is regression by name, but actually it has a categorical output. So it transforms the idea of a linear regression into categorical outputs. So logistic regression is the linear regression variant for categorical output. So it's a linear classifier actually. Yeah? So it should be listed up there in the linear models when we talk about classifiers. Yeah? Logistic regression is another variant of it's a different variant of support vector machines. Yeah, but in the same category of linear models. Okay. Good. Yeah, so in regression, just that you know, we typically have to again trade off overfitting and underfitting here. So first of all, we see here different models for the same data set here, so for the same observations. Yeah, so the X is the input, the Y is the output, for example. So that would be also here the case. So X is the input, Y is the output, yeah, which should be predicted. And of course, we could have different models here for these observations. So a linear model, for example, would be a classical case of underfitting in that case, because the model is too simple to grasp the relationship between X and Y, the input and the output, because it's just not a linear thing here. Yeah, so a polynomial model would be obviously better here. Yeah, with maybe a small polynomial, yeah, would be a good fitting, but we can also use a higher degree polynomial, and that it would be something like this here, would be which would decrease the error, the training error, but obviously that is a very, very complex model, so we probably are overfitting again here. Yeah, so we have the same problem with generalization and overfitting. So the more complex a model is, the better is the performance on the training, of course, but the higher the probability and the danger of overfitting, of course. Yeah. And this would be a polynomial of higher degree, which is a very, very complex model, maybe a very good training error, but probably overfitting. Yeah? So that is the general trend, which is a good fit here, even though it has not the best performance on the training set, obviously. Yeah? So that would be if we use polynomial models. If we use piecewise linear models, again we have the problem of underfitting, good fitting, and overfitting. So here again, a piecewise linear model where we just use one piece, one big partition for the same for the entire data set. In that case, just a linear model or a linear regression. That would be again underfitting because the model is just too coarse, too simple. Yeah, that would be a good fitting with just two partitions. Yeah, if we use multiple partitions, yeah, the input is partitioned, so the x-axis is partitioned into several intervals, and in each interval we apply linear regression. Yeah? So we have one interval from here to here, apply linear regression, one interval from here to here, apply linear regression, one interval from here to here, and so on and so on and so on. Yeah? And here, obviously, even though we approximate the input-output relationship very good, we have a very high number of intervals of pieces, and that is probably again overfitting, yeah, because the model gets extremely complex, and once again that is always typically a sign of overfitting. So here we just have two intervals, yeah, an interval from here to here, yeah, on the x-axis, and a linear model in this interval, and a linear model in the second interval, and that is probably a good fitting overall, which generalizes better than this one here. Okay, so the same as before, the more complex a model, the higher the probability to overfit actually to the training data. But we also have the problem between, or the trade-off between, bias and variance, which typically is solved by means of regularization methods, and we have to talk about regularization in the context of regression a little bit, at least, just that you get a feeling about the problem, that you know about the problem at least. Yeah. So what is it all about? Well, assume that the data generation process can be repeated. Yeah. So we see our data here, the blue points, and let's assume that we can repeat this observation generating process with a certain amount of randomness, of course, and we obtain for each of the repetitions, each of these data sets, we train or fit a model. Yeah? So all the data sets are a little bit different with a certain amount of randomness, and we fit different models on all these different data sets. Yeah? And then we talk about bias, which is the difference between the average prediction of these models that we fit to the different data sets and the correct value. Yeah? And the second one is the variance, which is the variability of the predictions of the different models. Yeah? Because the FIs would be a little bit different for the DIs, because the DIs, well, they have the same generating process, but they are a little bit, there's a little bit randomness added. Yeah? So they are not exactly the same observations. So we will have probably a little bit of variance if we compare the outputs of the different models that we learn on the different data sets. Yeah? And both are actually kind of, yeah, types of errors you see here. So and of course, if you look at the model complexity, well, the bias, if you have a very low complexity model, low complex model, then you typically have a very high bias but a low variance. Yeah? Why? Because, well, the difference between the average prediction of these models, if the model is very simple, the difference will be quite huge. Yeah? But the variability will be not very huge, because these models, since they are very simple, will probably predict more or less the same, even though there is some variance in the data sets during the learning. Yeah? So the variance will be low, but the bias will be high. And if we increase the model complexity, of course the variance will go up, yeah, because the models, the FIs, will be very specific to DI. Yeah? So the variability of the predictions of the different models will increase, so the variance will increase, but the bias, the difference between the average prediction of these models and the correct value, will of course decrease. Yeah? And both bias and variance are, of course, things that we don't want to have. So we have to carefully balance between those two types of errors in order to have a very generalized or the most generalized model. So the total expected prediction error should, of course, be minimized. We want to have a generalizing model, and that's why we have to carefully balance out those two different things.